Okay, so part two. We set out in the morning to take us from the Big Bang to planets. So that's where we're at. And then we're now going to go from planets to life. Then think about if there is life outside of Earth, so extraterrestrials, aliens. Spoiler alert, we don't know. But we will talk about how we're trying to know that and what we can make some sort of educated inferences or guesses about. And then we'll talk about the theology associated with alien life. So that's the roadmap for the next hour or so. What makes the origins of life such a difficult question to sort of wrap your head around, so the origins of life, how chemistry could turn into biology, is just how complex present-day life is. So when we are trying to figure out how that sort of life could emerge out of what seems like random chemical reactions, it seems like that would be really hard. And two of the things that is especially difficult to develop, has been sort of stumbling blocks in developing a solid theory for the origins of life, is on the one hand that the molecules that encode information in our cells, so the DNA and RNA, these are very big, very complicated, and extremely well-ordered molecules. And it is sort of difficult to even conceive how that could come into existence just by randomly sort of bringing different building blocks together. But as we'll see, you don't have to go all the way to randomness just because you don't have miracles. Slight side note, I think it's totally amazing that at the heart of life, there is something like an alphabet. But since we are, people of the word, like maybe we shouldn't be as amazed. I think it's awesome. So we have this really complicated information-carrying molecules that is at the heart of life. But that is also why we think that this is chemistry. In some sense, this is very complicated chemistry that is involved at the center of life, which is why one could at least have some basic idea that there was first chemistry and then biology. But in addition to these molecules being in themselves very complicated, the processes that goes on in cells is also incredibly complicated. Like even if you take the smallest sort of living things we have today, there's just tons of things going on that's sort of beyond belief. This, I'm going to see if the movie starts in a moment. This is a small motor protein. It's not a picture, it's an illustration, but it's an accurate illustration of a motor protein carrying a vesicle of material from one place to another in a cell. And let's see if that actually works. So this is what's going on in all of your cells all the time, but also in the cells of bacteria. So how this could come into existence, like sort of by chance, through sort of random chemical reactions, that is at the heart of the problem of the origins of life. And for those of you who wants to go and see the whole video, it's on YouTube. You can find it. I'll look up, I think I have the reference down here. So it's called Inner Life of a Cell. Amazing set of videos that were made at Harvard. So then the question comes, and this is something that you often hear in Christian circles, that the origins of life must have been a miracle. This is just too complicated to have happen naturally. The chances are too small that you can go from sort of random chemistry to biology. So that's like question number one that we're going to have to sort of face. Do we think that the origins of life was a miracle? What makes this a little bit harder, and this is not the only thing that's been suggested to be sort of miraculous when we think about different sort of scientific origins. As we talked about earlier, the solar system, Newton thought that had a miraculous sort of direct intervention from God to exist. And now we know that now we can explain it by these amazing laws of physics, which on their own, they are a bit mysterious, but at least once you have them, we can explain how planets form. Evolution would be another, where we used to think that every species had to be directly created by God. Now we know there is another explanation, so that's the theory of evolution. And the question is whether the origins of life also has that kind of natural explanation. What makes it a bit harder to give sort of a definitive answer is that for these other things that I just told you about, we know what that scientific theory and explanation is. We don't have a good explanation or a good scientific theory for the origins of life, which sort of leaves the idea that it might have been a direct intervention from God, at least for now, sort of a possibility. I don't think that that was what happened, and I will give you the outlines of what we think happened instead. But it is important to acknowledge that we have not figured out how you get from chemistry to biology. This is very much something that's being researched actively, but it's not something that scientists have figured out. So anyone who tells you that we know how life originated are, at best, simplifying. As we'll see, they're going to tell you something very similar to the story that I'm going to tell. But it is right now a story. It is not a scientific theory. So what makes me think that if we don't have a solid scientific theory, why do I think that it was not a miracle? I don't think it was a miracle because it doesn't have to be. And it seems like the way that God generally operates is through secondary causes. I mean, that is, we just spent a whole lecture looking at sort of the amazing dignity of creation, where all these secondary causes, all these things get to be part of co-creating sort of the universe. And now, when we get to the origins of life, why in some sense would it be different? The counter argument would be, well, it's different because in some sense it has to be. There's no way you can get biology out of chemistry. So it will be a little bit similar to, like, there are two things I said that in some sense had to be direct intervention. One is the origins of the entire universe, the entire created order. And the other is the origins of our souls. Those just cannot have a natural explanation. So the question is then, origins of life, which one of these two does it fit into? And all the people who would like to put it in that it could not happen, what they're going to give is basically an improbability argument, that it's so unlikely that you need a direct intervention. But that doesn't make it sort of philosophically impossible, right? That is not the same thing. Like when we think about, could our immortal souls have come about naturally? That is not the probability argument. It is, they couldn't, if something is material, it cannot come out of a material cause. Like that's a much more definitive no than saying that something is extremely improbable. Like, for example, the laws of nature, they seem very improbable, but they're not philosophically impossible. Like those are distinct things. So the first thing is to say is that, well, we can't rule out the miracle, but we don't need a miracle in that sort of strictest sense. The other reason, so I have sort of theological reasons to think that it's not a miracle. It seems like God prefers to work through secondary causes and in some sense imbue the nature with its causal powers and these laws that allow for new things to emerge rather than direct intervention. My other reason for thinking that it's not a miracle is that we are actually making some progress in understanding how this could have happened. So that's where I want to go next. This is a cartoon of what we think happened. So we start around 4.5 billion years ago with the formation of the Earth. Then you have a moon impact, which basically makes the Earth uninhabitable for a couple of 100 million years. Around 4.2 billion years ago, we have an Earth that is habitable in the sense that you can have liquid water on the surface. You have sort of a stable environment within which you could have life surviving if it has come into existence. Around, here it says 3.6. 3.7 is the current sort of oldest evidence, though it's not clear-cut evidence. So around 3.6, 3.7, 3.8 billion years ago, we have the first evidence for life here on Earth. By 3.5 billion years, the evidence is clear-cut, and everyone agrees. But there is some evidence going back all the way to 3.8 billion years ago. In between, then, this sort of first, or like the first life that has left any sort of evidence, and when life could possibly have come into existence, it's around 400, 500 million years. So the question is, what happened then? And this is a cartoon of what happened. You have the Earth. It has some water. It has some organic molecules. These organic molecules, they react with one another to form more complex ones, including the basic building blocks of RNA, DNA, and proteins. So we're talking about things like amino acids and other kinds of sort of prebiotic molecules. These building blocks, they start combining together to form these larger chains and larger structures that we associate with cells, with life, including something that looks like RNA. People prefer, or like there's a idea that, okay, we have these two kind of information-carrying molecules in cells, RNA and DNA. DNA is where information is stored mainly, and RNA has some storage capabilities, but also works to translate sort of DNA into action. There's an idea that maybe the first thing that existed was just RNA because it has these multiple things it can do. It can both store information, and it can, under some circumstances, also help to catalyze its own self-replication. So it can do sort of multiple things. So you develop something that is sort of living in this RNA world, and that through some sort of or like very early evolution then pushes you towards more efficient life, which takes over sort of the whole surface of the Earth by around 3.8 billion years ago. If we find any evidence, and so these are all bacteria-like things, they don't leave fossils. So if we find any evidence for life by 3.8 billion years ago, if this evidence turns out to be true, that means that 400 million years after life first came into existence, it was, or like where it could have come into existence, it was everywhere. This suggests to most scientists that origins of life happened pretty quickly. It happened sort of as soon as you had this stable hydrosphere, you started this sort of march towards life, and it happened pretty soon. None of these, I would say that most scientists would say that if you get here, if you get to the RNA world, you can probably figure out a way through evolution to push towards the kind of life we have today. This would be much simpler. It would not have the nice little guy carrying the package around in the cell. This would be much simpler kind of life. But at that point where you have this sort of replication going on, you could then get the same, like these analogous mechanisms to what we have today. Evolutionary pressure push you towards more efficient life. So the difficulty really comes, how do you sort this part out here when you really go from what's barely biology, from chemistry to what's barely biology. We can zoom in on that step, and that's just what's being done here now for the chemist in the room, showing things like a little bit more chemical looking. So step number one, we try to form these sort of very basic building blocks. This step is being figured out. And this was not the case 10, 20 years ago, that we had sort of a reasonable scheme for how to sort out this whole part here. But it turns out that there are reasonable environmental conditions that corresponding to the young Earth, which will give you basically all the building blocks that you need for life. And it won't give you that much extra junk. Like it seems like really that the building blocks that you have in your cell are kind of preferred products for at least some kinds of chemistry. And this is, I guess, point number one. Like many of the arguments you get of why the origins of life had to be miraculous are these probability arguments, which is that if you randomly put atoms together, there's no way you can get to this within the time frame and the size of the Earth. There's just like too many different ways you can combine atoms. But you don't have to do things randomly. That's where the laws of nature step in, or laws of chemistry in this case, that actually prefer some chemical bonds over others. It prefers there's some chemical interactions that are energetically preferable with the kind of laws of nature that we have. So this is not, just because it's not a miraculous process doesn't mean it has to be random, or at least not random in the sort of completely uncontrolled way. And I think that's an important distinction. And as I said, at least for these building blocks, there are millions of simple organic molecules that you could imagine this early chemistry forming. But at least under some settings, it seems like the kind of products that are forming are exactly the ones that ended up in our cells. So the laws of chemistry actually help you on this march towards biology. Where a lot of the action is right now is how to go from these simple building blocks to very short RNA-type molecules or short peptides. This also, I think, we are going in a good direction. There are many things we know now and we think can be done in some sense naturally that we couldn't 10 years ago. As I want to stress, this does not mean that this is a solved problem. By no means it is. But I think I have seen enough sort of progress going in this direction that another 50, maybe 100 years, I don't think it's going to be tomorrow, I think it's going to be decades, I think we're going to figure this out. I think we are going to figure out at least one plausible way to get from chemistry to biology. This is, I would say, is the intuition by the majority of scientists, but not by every single one of them. So there's definitely room for dissent. Though for most scientists, the dissent would not be that it's a miracle. It would be that this is actually a very unlikely process, and maybe it only happened once here on Earth. And if you have a very unlikely process, well, that's OK if you try it out hundreds of billions and billions of times. And the only reason that we are sitting here sort of pondering this is that we are the lucky planet. In some sense, we had to be for us to be sitting here. My suspicion is that this is actually a much more universal process, and we will find life elsewhere as well. But that is, we're going to talk more about that in a minute or two. So this general cartoon, I was saying that is where most scientists are. Where there is a substantial disagreement is where this happened. So if you want to have a chemistry, like you want to move from chemistry to biology, you need some source of energy to do that. And there are a couple of options that have been suggested. One of the most famous one is using lightning. There's a lot of energy in lightning. This is where you get these Urey-Milner experiments. That's what they use. What's been popularized in the past, I would say, decades are these underwater thermal vents where you get a lot of hot water and chemicals coming into the water, which produces a lot of chemistry. I would say somewhat unclear how useful of chemistry, but it certainly does a lot of chemistry. And as you maybe can tell from my tone, I don't think either of those are the right ones. Instead, the one that I favor is the one that's illustrated here, which are basically lakes and ponds. So where you have a landmass, you have a small lake, small pond, which is fed from space by impacts. You get some important reactants from space. And then you get most of your energy from the sun. So you get UV from the sun, and that would be your main source of energy. The reason that I favor this scenario is that is the environment where we actually do produce a lot of these prebiotic molecules that I said we had sort of figured out how to make. You need UV light to produce those, which is what, if you think that is the right way to get those small molecules, then it really pushes you to the surface of a planet. And that's what's illustrated here. So if you have water, you have access to UV, so you're close to the surface. You have some form of sulfur, and you have hydrogen cyanide. If you have those ingredients, you very readily form the right kinds of these sort of small to mid-sized organic molecules. And the hydrogen cyanide, very, very good to get life started, only became poisonous once we started relying on oxygen. So hydrogen cyanide and oxygen don't go together, but that was not how the first life, how the first life was doing its metabolism. So we have, as I said, we have gotten somewhere in thinking about how life could originate here on Earth. And that, of course, leads to the question if there's also life outside of it. This is actually, these two are earthly creatures. This one, obviously not. And I think the idea, the intuition is that if the origins of life is a natural event, if it was a natural event here on Earth, if we find another environment, such as the early Earth, we should expect to see an origins of life there as well. I mean, that is the general intuition. So a lot of the research right now, it's either trying to find directly detect some of the effects of life or directly detect signals from more intelligent life on the one hand, and on the other trying to predict how often do you get an environment that resembled the early Earth. So those are sort of the two avenues when that people go when they are thinking about the origins of life. Or the origins of life in other places, the existence of extraterrestrial life. The problem and the reason that we don't yet have an answer to that is that it's not that easy to study other planets if we go outside of the solar system. When we look at planets in the solar system, these are nearby. We can take gorgeous pictures of them, like here of Saturn. We cannot do that for planets around other stars. Instead, the way that we look for exoplanets is typically quite indirect. Actually, I would say with a few important exceptions, this is true. This is actually direct images of planets, but this is what they look like. You can see them move. But these are actually unresolved planets that are much larger than Jupiter. So we cannot see planets directly around other stars unless they are super big, young, and far away from their star. None of those would make them conducive to having life on them. These are almost like having little mini stars orbiting the big star at the center. But for any kind of normal planet, we have to look for them indirectly. And there are two main ways to do it. One is called the radial velocity method. It relies on the gravitational tugging from the planet on the stars. In both of these cases, we're going to look at the star. We're going to look at the effect of the planet on the star. One way is to take advantage of the fact that when a star is orbiting a planet, really both the star and the planets are orbiting the common center of gravity. So if you look at the star, you see it moving back and forth. Well, based on that, you can work out how massive of a planet is orbiting that star. So that's method number one. Method number two relies on the cases when the star, the planet, and us are in the same line of sight. So when the planet orbits the star, it dims the star a little bit. So we can look for that slight dimming. Both of these is pretty indirect methods, which makes it difficult to study the planets themselves. Not impossible, but difficult. But we have learned a lot from these methods. Perhaps the most important thing we have learned is that planets are incredibly common. There are more planets than stars in the galaxy. And since there are around 300 billion stars, that makes for a lot of billions of planets in our galaxy alone. And then there are hundreds of billions of galaxies. So again, if you want a lot of chances to get life going, there are at least a lot of planets on which you can do it. The second thing we have learned is that planets can be very different, both among themselves, but also compared to what we see in the solar system. So when we look at exoplanets, we have everything from sort of super Jupiters that are orbiting right next to their star to like small Neptunes, to even smaller lava planets and so on. Planets come in all kinds of flavors. So just because you have a planet doesn't mean you have a planet on which you can have life. So that's number 2. And here shows a distribution roughly of what kind of planets we have found so far. The main thing I want you to notice is that where you have the highest bars is right where there are no planets in the solar system. So the solar system, you have small rocky planets, you have big gas and ice planets. The most common planet we're finding is something in between. So what that is also telling us now, point number 3, is that our solar system is not typical. Doesn't mean that it's impossibly rare, but it's not the most common kind of planetary system there's out there. The kind of planets, though, that we are most interested in if we're thinking about life are planets that are similar to the Earth. And similar in a couple of different ways. But most importantly, they're about the same size, and they're sitting at a distance from their star where they're neither too hot nor too cold, but somewhere in between. And in between, what that means that they are at the right temperature to sustain liquid water, which we think is one of the fundamental requirements for life. So I'm happy to take discussions on whether that is a reasonable assumption or not. So then the question becomes, so how many of those do we have? We're not completely sure, like the estimates vary a bit, but it's something between a few percent and 10 to 20% of stars probably have a planet like the Earth around it. If we take the lower, if we go into the lower range of that, around 1% or so, that still gives several billions of those in this galaxy alone. So even if our solar system is not the most common, and these kind of Earth-like planets are not the most common, they're still common enough that there should be like many, many planets that are kind of similar to the Earth in terms of their size and their distance from their star compared to what we have in the solar system. And one of them that we have found is the TRAPPIST-1 system. TRAPPIST-1 is a small star that has 7 rocky planets orbiting it at different distances. And here is, you can see the light curves where it was discovered. So the flat line here is when you see just the light from the star. And then the planet passes in front, and you see this dip. And the planet goes, passes out of view from the star, and you see all the light from the star again. And in this case, 3 of these planets are in this so-called habitable zone, where it's the right temperature to sustain liquid water. What's special, though, about this one is that the star is so tiny, so it's so faint, so this whole system of planets fits well within the orbit of Mercury if it was sitting in our solar system. So even the ones that are similar are sometimes very different from the system that we're sitting in. But this is not the only thing that we need to have an ordinance of life. Remember that I gave the definition of the right temperature, to have liquid water. But then the question is, do you have water? So that's the first thing that we need to revisit. Whether a planet, like if we went to TRAPPIST-1, would one of those planets sitting in this habitable zone look something like this? Or would they be completely dry desert kind of planets? We actually already, in some sense, looked at this. We saw that water is one of the most common molecules in the universe, and that we often see it in the disks where planets are forming. So we actually think that it is going to be very common that planets do form with water. Like that is probably not going to be the bottleneck to have an ordinance of life. But the second thing that we want to consider is whether these water even, if they have water on them, whether these planets also have organics on them. The kind of building blocks of the building blocks that we need to get the organisms of life chemistry going. And here there are a couple of different ways you could try to sort that out. But one of them is to go back and think about how planets form and ask the question, well, there was always water around where the planets form. Are there also organic molecules around? And one of the ways we can do that is to turn our telescopes towards these protoplanetary disks and then go looking for water and organics in them. And this slide was totally misplaced. It was posted there two slides ago, just to tell you that based on the discussion we already had earlier, we might actually often run into the problem of having too much water rather than too little on these planets and not have any land mass where we could have these lakes and ponds. But back to the organics. So we can look at these disks using this ALMA telescope that we talked about before, which, remember, was millimeter wavelength light, which is very good at either inducing or allowing you to detect the rotations of molecules. So in this case, these are observations of these kind of disks, but now not looking at the total mass of the disks, but instead just focusing in on different molecules. So in this case, every row is a different object, and every column is a different molecule in these disks. So we have the capability of actually checking what kind of chemistry is available to planets as they are forming. And zooming in on just one of those molecules which we might be interested in, so hydrogen cyanide, which I told you was one of those molecules you want to have present if you want origins of life, we can see that that is actually a molecule that's very abundant in protoplanetary disks when we look for it. Bottom line, in addition to forming with access to water, we think most planets form with access to organic molecules. So if those two things are the only thing that's needed for life to originate, then life should be pretty common. Not as in it's on every planet or in every system, but if about 1% of these systems have a habitable planet, it might very well be that 1% of systems in the galaxy have some sort of life on it, if the origins of life is a universal and relatively straightforward process. So where the science is currently, planets are incredibly common. And including planets that are sort of potentially habitable in terms of just the right size and the right temperature are quite common. It seems, from as far as we can tell, that they often assemble in environments that are rich in water and organics. So when we put those things together, the planets that have sort of the basic conditions for an Earth-like origins of life are common. But we don't yet know if actual if planets that are actually inhabited are. And the reason we don't know, I said, is that looking for life directly on planets is hard because we're looking for planets in these kind of indirect ways. Now, there are plans to go looking for the signatures of life on exoplanets, as you could imagine, that a lot of astronomers are very excited about that prospect. And the main way that you would do this is taking into account the fact that living things, they interact with their environment in a couple of different ways. And one of the ways to do that is by emitting gases into the atmosphere. So plants emit oxygen, many kind of life forms emit methane, and so on. So if you go looking at if you can take a spectra of the atmosphere of a planet, you can compare that with a model of what you think that atmosphere should be like if there's no life around. You could infer whether it's a dead or an alive planet. As you might imagine, there are many potential ways to do this wrong, and like you can have the wrong model, right? So this is going to be a probability argument. But it's not a bad argument, and astronomers have started to think about how to deal with this uncertainty that we don't always have a perfect model of what sort of a lifeless planet should look like. So the idea is to build lots of models, first of all, of what kind of molecules can be produced by life, what kind of molecules can be produced without life, including from volcanoes, meteoritic impacts, and so on. The data that we're going to get is going to be very limited. To start with just spectra, maybe eventually we'll start seeing some images as well. And then how do we, when we compare the expected sort of signature with a actual one, how do we then quantify how sure we are that this is a living or a dead planet? So these are kind of things that are being worked out right now. This might sound like it's going to be sort of very insecure, like kind of results. But there are some molecules that if you find like groups of molecules, that you can be much more certain than if you find a single one. So an example. Here on Earth, all the methane that's in the atmosphere comes from life. If you find methane on another planet, though, there are other possible ways you could be producing that methane. If you have some hydrogen in the atmosphere, we don't have really any hydrogen in the atmosphere, you could have that react with CO or CO2 and form methane that way. But if you find both methane and O2, then it becomes trickier to come up with a model that doesn't have life to produce those two molecules together. If those two molecules are left to their own devices, they're going to react and destroy one another. You need to have both of them being produced to see both of them in an atmosphere. And there are no natural processes we know of that would produce both of them. So that's mainly what we're trying to do, is look not just for single molecules, but sort of constellations of molecules that seem like the only way you can really get them is to have life on the planet. So we have some of the theory spelled out. The problem is we don't yet have the telescopes that are sensitive enough to do this for Earth-like planets. We can do study atmospheres of some exoplanets. This is one with the James Webb Space Telescope. So the James Webb Space Telescope is really good basically for looking very far into the distance. So we looked at some cosmological results and looking at things really nearby that have really weak signals. That is where the James Webb Space Telescope really shines. And because the way we observe exoplanets right now is that we see the planet going in front of the star. It's a tiny dip. So it's a weak signal. And then what we're doing on top of that is that we look how deep is that dip if we look at it at different wavelengths. And so it's sort of a weak signal on top of a weak signal. And the result is what you're seeing here. As you're stepping through different wavelengths, you see either a dip that's bigger or smaller. And based on that, you can infer whether a molecule is present in the atmosphere or not. In this case, clearly we see water, we see a lot of CO2, for example. But this spectra here is of a Jupiter-sized planet. That is a much bigger signal than you would get from an Earth-sized one. And this we can do. We might even be able to do it for Neptune-sized planets, though it's a bit of a struggle. But even with James Webb, which is this beautiful, enormous new telescope, doing this kind of work for Earth-sized planets is going to be incredibly difficult. And we are probably going to need a whole new set of telescopes to actually go for them. So it's going to be incredibly difficult to do anything for Earth-sized planets. Looking for minor atmospheric constituents produced by life is basically impossible. We need a new telescope to do that. So not technically impossible to do this work, just difficult, which is the important thing. Like if we decided that this was a civilizational priority, we could do this in a 10-year timescale. We just haven't done that. In the meantime, we could look closer to home as well. There are places in our solar system where there could be life, or at least could have been life in the past. Mars has been a favorite target for a long time. Mine, however, is this little moon. Here it looks like it's the same size like Mars. Really, it's about that size. So it's a very tiny moon. It's orbiting Saturn. It's icy. But underneath this ice is an ocean of liquid water that contains organics. So if all you need are organics and water, there should be life here. If you need UV light as well, as I think we did on Earth, you're not going to have life. But we don't know that for sure. Like, this is just my favorite theory. It is not at all clear that that's the only way for life to originate. And again, what's really exciting about Enceladus is that it has these plumes, so it's spewing some of the water into space. You can just fly by and check it out. This is something I think NASA will do in the next 10 to 20 years, so at least we will have a better idea within our solar system of whether there's life outside of Earth. So that's the sort of where the science currently stands on any kind of life. At this point, we haven't thought about what kind of life it is. I've been sort of assuming there's more like bacterial life rather than anything bigger. So we'll come to the bigger things in a moment. But I think it's good to just pause and think about, even for this kind of bacterial extraterrestrials, are there any sort of theological implications or any theological lessons you would want to bring into discussions of that possibility? I don't think there are any sort of real theological hurdles here. When we get to rational extraterrestrials, I think that gets more interesting. But for the moment, I think we are only pondering whether the abundance of life goes beyond the Earth or not. And I see no reason why it shouldn't. But I also don't really see any reason that it has to. I can imagine a universe where, in some sense, the whole universe was created to allow life to originate on this one place. But I also think that, considering the abundance of life here on Earth, and that it seems like the laws of nature made it very easy for life to originate here, that it's quite likely that we see life elsewhere as well. And I don't think there is any sort of like even a very literal reading of Genesis, I don't see any reason why that should be sort of theologically so prohibited. On the contrary, it seems like sort of the joy of creation that I think gets through in Genesis would, if anything, make one lean toward that that sort of creative power goes far beyond the Earth in terms of filling the universe with life. But there is also the possibility that this Earth is it in terms of life. That is a somewhat colder and emptier universe than the one that's sort of overflowing with life everywhere. In that case, we would be the ark carrying all life with us on this planet through space and time. I mean, it's a beautiful vision itself, which I think really allows us to focus on the fragility and sort of the beauty on being this fragile planet that is carrying all of life with it. So I think also a place that is fruitful for theological reflection. But we need to march on towards the potentially more controversial ETs. So this was the bacteria. The next step is animals. And here just from a scientific point of view, we want to ask ourselves, does Darwinian evolution always lead to animals? Since that's sort of a precondition to having intelligent animals or rational animals. And I would say the answer is not clear. If we look at the history of Earth, it looks like this. So this is where we were spending all our time before with the origins of life, around 4.5 to 4 billion years ago. This is where we're sitting today. All animal life happened in this last sort of green period here. For the most of the Earth's history, what we had was bacterial or even simpler life. So when we look at it just from a time argument, it seems like the bottleneck towards getting to animals was not actually the origins of life, which seemed to have happened very quickly, but to make the jump from single-cell life to truly multicellular kind of animal life. That took a long time to happen here on Earth. And the fact that it took a long time suggests that it's in some sense difficult. There's not something that you can take for granted that happens all the time. We may very well have many planets in the galaxy that have life on them, but that have single-cell life rather than having made this sort of animal jump. So even from a scientific point of view, it's not obvious that you need to go from origins of life to sort of rational beings with their potential theological consequences. Should we expect extraterrestrial animal life, or why might we expect it? Well, I think we might expect it from a similar reason that we should expect, or at least interpret, the richness of animal life that we see here on Earth, which is something that has been contemplated for a long time. Thomas Aquinas very eloquently talks about this as like this richness of a creation as a way to show forth God in ways that would otherwise not be possible, where every creature shows some aspect of God that only that creature could show. And therefore, in some sense, the more diversity, the more kind of creatures you have, the more kind of sides or aspects of God are revealed to you. And I think that is certainly something that we could take also beyond the Earth when thinking about why should we expect there to be this rich animal life that goes beyond what we see here on Earth. This, of course, kind of assumes that we'll one day get to interact with them to get this theological sort of meaning from them, unless there are some other rational animals on those planets that are learning the same lessons. Which brings us to the potential of rational extraterrestrials, which, I mean, is in some sense what this whole lecture was going for. Like this is what the question is really about. So again, I think it's good to start with the science. Should we expect, just from evolutionary processes, intelligent animals to develop? So not rational, but intelligent. Well, here on Earth, many kinds of intelligent animals have developed through Darwinian evolution. We're talking some birds are pretty intelligent, dolphins are intelligent, and primates, most of all. And our Homo sapiens was far from the only very intelligent primate to develop in the past sort of millions of years. We are part of this family tree of highly intelligent animals. So it seems like there is pretty strong evolutionary pressure for at least some animals to develop intelligence, imagination, emotions, and many of the things that we think about when we think about what intelligence is. We are more than intelligent animals, and we'll get to that in a moment. But if it's a precondition for becoming rationally ensouled that you have this sort of animal intelligence, it seems like at least that precondition might develop quite naturally and quite often once you have animal life happening. What happened then, this is also sort of archaeology or looking into sort of our past, is that sort of hundreds of thousands of years ago, our species developed, so Homo sapiens. But then it took another couple of 100,000 of years, or at least 100,000 years within our species, our subspecies, Homo sapiens, before we started seeing the kind of habits, the kind of activities that we really associate with humanness. So I'm thinking about things like cave paintings, really advanced tool development that develops over time, what seems to be like religious ritual where we see burials with burial goods and things like that, things that suggest an afterlife. These things almost exclusively, not completely, but almost exclusively developed within Homo sapiens, and it happened tens of thousands of years ago. Somewhere between 50 and 30,000 years ago is when most of this activity happened. This is just to say that it's not clear that when we're thinking about sort of theologically human beings, that those are exactly the same as the biologically human. That our species goes back hundreds of thousands of years, but we're talking about what's recognizably human activities. We can't tell if that goes back more than sort of 30 to 50,000 years ago. But by the time you have cave paintings, I think there's no doubt that we're talking about someone who is both biologically and theologically human, that this is a rationally ensouled being. What we can, I think, discern by philosophy and know by faith is that to be able to do these kind of activities with this abstract kind of thinking, this kind of art, that takes an immaterial soul. And an immaterial soul is not something that develops naturally through evolution. That is something that is given to each human directly from God. That also means that to have rational extraterrestrials, they too need to have that direct creative souls given to them from God, which I guess should be comforting, that they're not going to sort of happen, not even by accident, but not even just through sort of the laws of nature. There's an active program to look for those. They don't call them rational, they call them intelligent, which I think is the wrong word to use. I would call this the search for extraterrestrial rational life rather than intelligent. Because if you have, these are searches for technological signatures, radio waves, and things like that. And if you're doing science, you have a rational soul. These kind of programs, as far as I know, have not yielded any results yet. But of course, there are other sort of reports in the media and such that would suggest otherwise. We can have a discussion about that if you want to. But there is a real scientific search for this, I guess, is the important thing. This is not sort of a crazy thing to want to go looking for. Once you have established that origins of life is possible, maybe even plausible on other planets, animal life seems at least some of the time follow this bacterial or single cell life. And intelligent animal life develops naturally. And if you only think that we are some intelligent animal machines, that's all you need. I don't believe that is true. I think we are rational animals. But in either case, this is not an unreasonable kind of scientific project. And yes, that was what I was saying about that these are not purely intelligent extraterrestrials. They're rational. It means they are specially created. So what do we make of this sort of theologically? So I think there are two concerns that are typically brought up. One is how we think about the relationship between God and our hypothetical rational aliens, and how that relationship sort of affects the relationship we have with God. If you look at Genesis, it seems like we are sort of the pinnacle of creation. We're created in the image and likeness of God. We have this very particular friendship with God. Is that somehow threatened if we introduce our hypothetical aliens? I don't think that is the case. There is, I think, no reason to doubt that sort of an infinite God can't have this sort of infinitely loving relationships with more than one rational species. And I think you can think about Genesis either as applying it's our story, like ours, it's also this love story with God. That is what that is telling. So it's not strange that it's focusing on humanity. Or I think there's another reading which is a bit more universalist, which is that the pinnacle of creation is the creation of this rational animal that spans this chasm between the material and immaterial order. and that we are one example of that sort of pinnacle of the created material world. One reason why I think it's that we don't need in any way to feel like our relationship is threatened is we already know that there is one other kind of rational, intelligent life out there. And we have seen this. I promised there would be some more Italian art. We have seen these intelligences in our history as well. And when angels show up, they do things to help our relationship with God rather than to in any way threaten it. See, there might be another angel coming. Yeah. But I think where the real Simone Martini, wonderful early Renaissance, but where the real, I think, potential obstacle is when we're thinking about the salvation of these hypothetical aliens. We are saved, we're brought back into friendship with God through the incarnation of the second person of the Trinity as a human being. This is an extraordinary it's difficult to think about any more extraordinary event than for God stepping into creation to come rescuing us. So the question is, what happens to our alien brothers and sisters if they fall as well? Will they be saved too? And in that case, how? So let's ponder that together. Could there be a second incarnation? Could we have an alien incarnation? Maybe. So this is another excerpt from Thomas. And when he ponders the question, could there be another incarnation? And he's not thinking about an alien race. He's thinking about in time here on Earth. And he says, absolutely. It's not like God lost the power to become incarnate because he became incarnate once. And it's not just the second person, but maybe the first person and the third person could also become incarnate. There's nothing that says that God has lost that power. However, this did not mean that Thomas Aquinas thought that there had been another incarnation. And my feeling is that he would find that quite unfitting to have more than one happening here on Earth, and he was thinking beyond Earth. I know I go back and forth, but I think probably not. That this just seems, and when you think about the incarnation, it does seem like one of those events that is a one-time kind of thing, rather than sort of a multiple events, one for each time that some race falls. But I'm getting ahead of myself a little bit because I want to do this a bit more systematically, thinking about what are the options for our hypothetical aliens. Could they be saved? Well, there are 5 options as far as I can tell. Option 1, they never fell. Perhaps we live in a universe which are full of extraterrestrial aliens that are looking upon us in absolute astonishment, and not of the good kind. That we're like, you got to do whatever, like you got the whole, basically, of creation. You could do and learn and flourish in all the ways you wanted, except don't eat the one fruit. And 2 minutes later, it looks really tasty. And that might be it. However, I would say, like, speaking against that is that we know that the humans are not the only creatures to have fallen. We know that a portion of the angels fell as well. And that might suggest that even if it's not the norm to fall away from God, that it is also not, we are not the only ones if we have more of these rational animals around. So second option, they fell and God did not save them. I think this is something that at least I sort of intuitively react very strongly against. I mean, in our own salvation history, the ridiculous measure, and not ridiculous in the good way, the ridiculous measures that God took to save us and bring us back into friendship would suggest that this is something that he does, that he loves his creatures. But I think sometimes we tend to think that we are sometimes more worthy or being pursued than we really are, and that it is sort of natural for God to go after us, rather than to wonder that he did it in the first place. There are some theologians who think that maybe Neanderthals were in some sense theologically human, but were not brought back into friendship with God. We don't have that idea that we see that salvation history with them. So while I would like to take this off the table, I'm not 100% sure that it is the right thing to do. But the 99% of me is going to cross this one out and think that if God came after us in this way, he probably would do it for other people as well. So option 3, they were saved through the same incarnation that saved us. This would be supported by, I think, the intuition that probably most of us have, that God stepping into his creation is this sort of momentous kind of event that kind of similar, sometimes, with the creation of the universe as a whole. It's not the kind of thing like the origins of life that might happen multiple times. Now, this is an intuition. It's not something that is theologically proven. The problem you run into, I would say, is twofold. One is that how would that happen? What mechanisms would people like on a different planet be saved through? How would they know that they had been saved if we have never communicated with them? You can imagine maybe some of that being overcome. There are messengers that are not humans that could be sent to other places too and tell them the good news. But the other one is that I think there are multiple places in especially the New Testament and Paul's letters and so on that emphasize both the spiritual and biological connection between Adam and Jesus of Nazareth. That it matters that he's not just a created thing, he is a human that is our brother. And that you lose that if you have this happening on a planet far, far away that you have no sort of material connection to. So if we take sort of the material and the body seriously, that would suggest that the incarnation, it was important that it happened to us here. And if it was important it happened to us, well, then it would seem to be important also for our hypothetical alien race. So there are a couple of problems here. That leads us to the fourth problem, that they were saved through some other means. Maybe their own incarnation, which we just looked at, is at least theologically seems possible. And it's not like you need an incarnation. God could have chosen to save us in other ways. If you look again at Thomas Aquinas, he talks about this as this was the most fitting way. And that's why he chose to save us through the incarnation. He has a sort of list of reasons why it was fitting. But it is not something that had to happen. And God could save this alien race through some other means. I would say the problem here is that if the incarnation was the most fitting, then why did we get the most fitting way and they get sort of the substandard way? That seems not fair. So this has led some, and on some days also me, to get to the option 5, that they don't exist. We might very well live in a universe that's full of life without being full of rational life. And we might be the one example, again, of this sort of a bridge between the material and immaterial order. And with that, I will stop and take any questions.
All right, friends, we have time for about 15 minutes of questions. Who would like to go first? I got you.
So, and I don't, in the question of extraterrestrial rational life,
Yes.
how would that, I guess, be reconciled with the encyclical Humani Generis, where Pope Pius XII condemned polygenism, that other humans were created after Adam and Eve that were not descended from Adam and Eve. If that's what the definition of rational life is being descended from Adam and Eve.
So I don't know the encyclical well enough, but I assume that what he focused on was earthly human life rather than also rolling out extraterrestrial life. And if that's the case, I think you definitely have the option to ponder whether it could be polygenesis that goes beyond the Earth. So I think there are there's liberty there in how to read that, or like freedom, theological freedom. But I think one should take serious the arguments that are being made there on why, like it's worth digging into, like why these arguments were made and which one of those would only apply to earthly life and which one might also apply to alien life. And I just don't know the encyclical well enough to know which ones falls into which camp there.
All right,
Yeah,
go ahead.
just quickly, and we're going to have a chance to talk a little bit more about that when we hear from Dan tomorrow. I'm just kind of keep us all on the program. I would add, though, that it's not apparent, no pun intended, that Humani Generis was about saying that polygenism is absolutely irreconcilable with the Catholic faith. In fact, we have good evidence from the drafts of the encyclical that at first it was expressed that way and then was changed. And we now know, thanks to the research of a great Catholic scholar by the name of Kenneth Kemp, that when the Pope was actually approached by cardinals to give a deeper explanation and maybe say, okay, yeah, what I really meant to say was it's absolutely irreconcilable with the Catholic faith, he told them, no, I expressed it the way that I wanted it expressed. So it has not been condemned. But what we have been cautioned is that since monogenism has always been assumed in every expression of original sin and what we mean by the fall and original sin, that there needs to be great caution as we begin to think about that, because the dogma of original sin is irreformable in a matter of revelation. Yeah.
Thank you.
Just very briefly, like a suggestion on number 3 up there. You know, there's a particularity and a universality kind of combined in salvation. You have Jesus becomes an Israelite, a Jew, and you have Gentiles involved in it. So, and he doesn't come incarnate in everybody's group, but just in one, and everybody shares in that. So perhaps that could be just something to throw in there as a possibility. There could be kind of a particularity that extends out to universality.
No, absolutely. And when I give a slightly longer talk about that, I like digging into the fact that I think what in some sense support this is that I think God seems to have been very fond of starting with a small seed in salvation history, starting with Abraham and the Jewish people, then with the one person, of course, of Jesus Christ, and that even here on earth, some of the problems I brought up was sort of the communication problem. You have had even here on earth where have been civilizations that for thousands of years have been sort of separate from sort of the good news, and sort of when we're thinking about how they could be saved, in some sense we run into a similar problem, and there are some stories about how they seem to have had supernatural communications, right? So no, absolutely, I think it's a really good point. So thank you for bringing it up.
This was incredibly fascinating, so thank you. And I'm almost sorry to not ask a question about alien life. But just briefly, to go back to those initial building blocks of life on Earth, if we think that they did originate in lakes, do we expect to see traces of that still today if we go look at lakes and find those pieces? Or do we think the conditions are so different now that we wouldn't expect to find it?
It's a great question. So here on Earth, life has unfortunately polluted everything. So it's very difficult to find traces of what the chemistry could have been like beforehand. But 4 billion years ago, Mars and Earth looked much more similar than they do today. Mars had water. Mars probably had the same organic chemistry going on that the Earth did. So one of the things that the current mission that is at Mars is looking for is actually looking at sort of ancient Martian lakes to see if there is evidence for that kind of chemistry there, where if life developed, it seemed like it was pretty short-lived. So where there should be more sort of evidence left over from this sort of pre-life kind of period.
Looking at, again, the formation of early molecules, and the Miller-Urey experiment seems to be in every standard biology textbook. And I know you kind of just answered this, but do we have any experimentation to try and reproduce the pond lake theory or not?
Yes, I should say that there are experiments that are trying all of these different theories. So there are still experiments that are looking, when I would say, better improved ways to think about lightning as a form of energy to get sort of elements from the atmosphere into a watery body where you can have some interesting chemistry. There are experiments that are trying to simulate these thermal events. But I would say the most successful experiments today are the ones that are trying to simulate these kind of shallow ponds with the UV light and the hydrogen cyanide and the sulfur, and that's why I favorite. So I think it's just the experiment. It's really very beautiful organic chemistry experiments that have brought us those evidence.
Thanks.
You talked about, right, so we don't have the kind of resolution to detect, like, for smaller planets. And you talked about needing new telescopes. Could you speak a little about, like, are we talking about, like, new kinds of telescopes that we haven't even imagined yet, just more and more bigger radio telescopes, or what kind of telescopes?
The good news is that I don't think we need new physics. It is really an engineering problem. Like, I think we know what we need to do. It's just very difficult and very expensive. So there are two ways that you can go about this. One is to continue to do this kind of transit measurements at optical and infrared wavelengths, where you're looking at the sort of the change in the signal as a planet goes in front of the star. That is still what the next generation of telescopes will try to do. They will just be like bigger and more sensitive. They might get there, but I think there is a growing suspicion that they might not, based on the early James Webb Space Telescopes. And what we really will need to be able to do is to take those direct images of the planets, like I showed with this giant Jupiters orbiting their star, where you block out the light of the star so you can see the faint light from the planets. To do that, you will need to have a space telescope that's very big, and then flying in formation in front of it, you'll need to have another, like, basically sort of a blocked aperture that allow you to block out the light from the star while allowing you to still see what's going on around it. And again, it's an engineering problem. It is not a physics problem. If we decided as a civilization that this was worth spending, I don't know, James Webb cost like tens, maybe $100 billion, which is a lot of money, but it's not like it's the majority of the US economy. Like, we could do this if we wanted to. I'm not saying that it should, but we could. Actually, if you give me like $5 billion, I'll get you life on Enceladus. So, so it is an engineering problem. We know what we need to do, but it's going to take tens of years to build it, to get the money and stuff.
Are we talking infrared? And when you say big, James Webb big?
So you're going to need bigger to just be more gathering more light. You'll probably, I mean, there are different ideas, and it depends on how, if the sensors continue to get better and so on. But you'll need bigger, so you'll need to assemble it in space probably instead of shooting it up in one piece. And so it will be an engineering challenge. I'm not saying it won't be an engineering challenge, but it's not, I don't think at all it's impossible. So it depends what kind of planet and what kind of planet star system, whether it's best to go in the infrared or in the optical. So there are pros and cons with both. The next one will probably be an optical one, so going back into the optical, but the one after that, which would be the one where you look for these molecules, probably more in the infrared.
When you were showing the evolution towards life, how is life defined in terms of biology or in terms of consciousness and rationality?
So life, that does not presuppose consciousness and rationality, right? So we're talking about bacteria. Does it have metabolism? Can it transmit information to the next generation? Like those are kind of very basic things that we are worried about when it comes to just life. There's not this single, everyone agrees upon kind of definition, but metabolism, information transfer, that you have something that's separate from its environment. Once you have those things, most people would be happy to call it life. Once we start getting to intelligent animal life, we seem to have something like consciousness, though it's a little bit difficult to know. We always run into the risk of sort of humanizing animals, but we see imagination, we see emotions, we see dreams, we see self-awareness. So there's at least a basic form of consciousness seems to be there, or with intelligent animals. So that would be part, I think, of sort of animal intelligence. And then rationality, then we're really talking about abstract thinking, which of course then impacts all the other things. A rational animal does have, in some sense, animal imagination, animal emotions, but they become a kind of rational emotions and rational imagination because we have a rational soul. So there's some analogy between the two, but they're not the same. So I don't know. So if we're talking about sort of intelligent animals, I would say that's where consciousness comes in. And then we talk about rational animals. Well, that's where the humans' rational souls come in.
You mentioned that the leap from a single-cell organism to a multi-cell organism was not a small one. Do you have any indications as to what sort of indicators you're looking for that jump?
Yeah, so I guess it's like an important caveat is that we see cellular sort of cooperation much earlier than that. So we see these large bacterial mats happening early on where sort of multiple sort of single-cell organisms, they start sort of working together in different ways. But actual animals, like multicellular organisms that reproduce new multicellular organisms, that for some reasons that is not, I would say, very well understood, takes a very long time to develop. And I don't know if there's a good answer of, first of all, why it didn't happen, and then why it happened. That both are things that people are researching and trying to understand. It seems like it might have been some coincidences with the oxygenation, but it is not obvious that those are sort of causally connected. So as far as I know, it is not the solved problem. Both why it happened and why it didn't happen sooner.
I have a question, Karin, and
Yes.
it's actually the most recent SCS conference. There was a presentation by Luke Yeager
Yeah.
on the.
Was I still there for that?
No, you weren't.
Okay, good.
But anyway, well, then maybe you can't answer the question. I was hoping you were familiar with his work, but he was doing a lot of stuff about the things that they've discovered about spontaneous organization of molecules and that kind of thing towards the direction of life, which I thought was interesting. So the video is on the Society of Catholic Scientists website, but I was going to see if it was something you would endorse or not. But anyway,
Yeah. So
can't answer that question. That's okay.
I can't endorse exactly what he said or not endorse because I don't know. But generally, I think what he says is very consistent with what I have seen from others and also what I was talking about here, which is that there is, like we often see this problem origins of life presented as either randomness or miraculous.
Yeah.
While I think what's really going on is this, that we're going to find out that the laws of chemistry in some sense are just as amazing as the laws of physics in directing how the universe develops in interesting ways. And I think we're already seeing signs of it, both in the formation of these like small molecules, how they seem to prefer to organize in ways that starts resembling something that we would associate with sort of this march towards life. And that I think there's some really interesting things to discover in the laws of chemistry in the coming years, and that we don't have to do this either or. And I think that's where a lot of sort of science and religion conflicts happen, is that there's this like false binaries, and I think this is one of them, even though we can't be as sure because we haven't actually solved the scientific problem, but I suspect it's going to be another one of them.
We have time for one more question, if there is one. Wonderful. Would you join? Oh, ooh, snuck in at the end. Go ahead.
Sorry to sneak in here. I was trying to phrase it in my head, so if this is a mess, I'm sorry. Do you think that, given how we've gone from chemistry to biology on Earth, that we were still studying that, as we look to exoplanets and different, beyond Earth, I guess, do you expect or to see life forming in the same way, or different starting points, different ending points, different environmental pressures? That's the best way I have of phrasing it. Sorry.
I mean, I think it's a very good question, and one that we haven't really touched upon. I mean, I just said that we need water and organics to start with, and you all politely nodded, and we moved on. I think there are good reasons for it. It's not just because they're Earth-centric. Water, as I said, is one of the most abundant molecules in the universe. It's an excellent solvent. I think most life is going to be water-based, just based on that alone. We might find that there are other life that are based on some other solvent. I don't think it's going to be very common. And if that's the case, the chemistry is going to look very different. Still going to be based on organic chemistry, but you just need a very different chemistry at that point to even form cell membranes, for example. But if it is water-based, and if this UV-driven chemistry is what caused the origins of life here, sort of as the most foundational layer, then life on other planets might not be that different at the sort of the molecular layer, which is a bit strange. I mean, I think we are often thinking that it should be sort of totally different. So my suspicion is that we might find that alien life, if we find it, is quite similar at the sort of the basic building blocks molecular layer. If it evolves into animal life, I think we'll also see a lot of similarities. Just based on that here on Earth, evolution has multiple times developed limbs, has developed eyes. I mean, you need those things to do and see things once you start being an intelligent animal. So we might very well see things molecularly similar, sort of looks kind of similar at the macroscopic level, and then you have most of the differences as sort of the intermediary layer, if that makes sense.
Can I ask a little follow-up? So, would we be looking at similar concentrations of those basic elements, or I know that can throw conformations a lot.
So it seems that the kind of elemental composition we have here on Earth seems like it might be pretty normal for this kind of planet from what we know currently. But we don't know that much about sort of Earth analogs or Earth-like planets. So I would say it seems like, I would say that's where the hypothesis would be that it is pretty similar. But it is something that we would need to actually confirm with observations.